Many years ago, Archimedes discovered buoyancy force. What the buoyancy force is? Look at this boat. It's partially submerged in water, on its anyway floated on the liquid. There is a force acting on that, which is called the buoyancy force or Archimedes force, which can cancel even the weight. For this case, the other is the balloon, which is fully submerged in air. And there is a buoyancy force acting on the balloon, which can easily be even greater than W, and the balloon can lift up. Sometimes the buoyancy force is not enough to cancel the weight, and the object will sink. So let's have three different distinguished cases and then continue finding the formula for that. First of all, the floated object, in which, as you see, the object is partially submerged and partially unsubmerged. The next is the fully submerged object like a submarine or maybe fish, which is suspended in the liquid. Here also we have a buoyancy force equal to W, can cancel the weight, but anyway, the object is heavy, so it can suspend in the liquid. But if the object is much, much heavier than that, I will tell you what do I mean by heavy. It's about the density. It will sink like a piece of metal or a stone. And the sunk object actually also is acted by a buoyancy force, but it's not enough to hold the object. So it needs a help. So in the first case, the buoyancy force is equal to W and opposite to that, of course. The second case, again, the buoyancy force is W. But the last, no. In this case, the buoyancy force is less than W. Anyway, how to find the buoyancy force? What's the reason of the buoyancy force? Basically, the reason is displacing the liquid or gas. When the object is submerged, partially or fully submerged in the liquid, or in general in a fluid, it displaces part of that. And due to that displacement, it's acted by the buoyancy force. Okay, let's go through an experiment and then learn it. The setting of experiment is very easy. Here I have a beaker fully filled with a liquid of density rho, an object of density rho prime. It will shortly be submerged, partially submerged in the liquid. And as the beaker is fully filled, the extra liquid, due to that submerging, uh, normally it's collected over the other empty beaker on the weighting scale. And this weighting scale can measure the weight of the displaced liquid. So I submerge the object and then I collect the extra volume, I mean the displaced liquid, and simultaneously I can measure the buoyancy force. Buoyancy force acted on the object when I submerge it here is surprisingly equal to the weight of this displaced liquid. And it's very interesting. So Archimedes expressed his idea about this experiment. The upward buoyancy force, sometimes it's called upthrust force or Archimedes force, on the object completely or partially submerged in a fluid is equal to the weight of a fluid displaced by the object. Exactly here. How to find the buoyancy force here? I mean the weight of the displaced liquid. It's very easy. Let's say the submerged part has a volume of V1. So I expect the displaced liquid to have the same volume, V1. On the other hand, I know that the density of liquid is going to be mass of the liquid divided by the volume. Volume of the displaced liquid is V1. So mass of the displaced liquid is going to be rho, density of liquid, multiplied by V1. And here I will find the buoyancy force easily by mg, mass of the displaced liquid multiplied by g. But what the mass is, rho, V1, and g. Done. This is the buoyancy force. So in short, the buoyancy force is equal to the weight of the displaced liquid. This weight is found by a multiplication of three different factors. First is the density of liquid, second is the gravitational acceleration you are familiar with, and finally the volume of the displaced fluid. When the object is fully submerged in the liquid, the volume of the displaced liquid is equal to the volume of the object. But it's not always correct. Sometimes the object is partially submerged. So here we used exactly the volume of the submerged part of the object, which is equal always to the volume of the displaced liquid. Let's answer this question. A wooden block with a submerged volume of 0.02 cubic meter is floating on water. If the density of the water is given to be 1000 kilogram per cubic meter, what is the buoyant force acting on the block? G is 10. Okay, the buoyant force acting on the block is supposed to be equal to the weight of the displaced liquid. Rho is the density of water here as the fluid. G is the gravitational acceleration given to be 10. And V is the volume of the displaced liquid. Here, the volume of the submerged part of the object. Here, exactly here. This volume is given to be 0.02. So I plug in the values accordingly. This is going to be 0.2 multiplied by 1000 is 200. So it's 200 Newton, the buoyancy force acting on the object. Here we have a very elegant point. Can I say this 200 Newton is exactly equal to the weight of the block? On the other hand, yeah, of course you can. In this case, yes, because the object is floating on the liquid, so the buoyancy force can cancel the weight, and it already has canceled it. So it seems to be yes, they are equal. But can I say always the buoyancy force is equal to weight? No, it's not always correct. When the object has a very high density, I will explain it shortly, it will sink. And a sunk object cannot have enough buoyancy force to cancel its weight. So it's not equal. But in this case, yes. Let's continue. For a floating object, if the density of the object is given to be rho prime and the density of the liquid is rho, I expect the weight to be equal and opposite to buoyancy force. Yes, buoyancy force in this case, as I explained, can cancel the weight. So Fp is equal to W. On the other hand, the W is the weight of the object, is the density of the object times the volume of the object times G. But the volume of the object is, first density of the object is rho prime here. So it's rho prime. Volume of the object is the total volume of the submerged and unsubmerged part. Let's say the submerged part has the volume of V1 and the unsubmerged part has a volume of V2. So here in the parentheses I fill it with V1 plus V2. This is the right side of this equation. Left side, the buoyancy force, is the weight of the displaced liquid. It's going to be mass of the displaced liquid times G. Mass of the displaced liquid is the density of liquid times the volume of the displaced liquid, which is equal to V1. It's expected to be V1, the displaced liquid. So I can easily substitute the values like that. Density of liquid times the volume of the displaced liquid or the volume of the submerged part. On the right side, rho prime, density of the object, volume of the object. And both sides, we have G. We can drop the G, it's not that important. And here I can rearrange the equation like that. Let's say it's the rho prime over rho to be V1 divided by V1 plus V2. Density of the object divided by density of liquid is equal to the volume of the submerged part of the object divided by the total volume of the object. Okay, what's the benefit of this relation? I will explain it shortly. Just let's solve a problem to know its application, and then I will explain the benefits. A wooden block with a weight of 20 Newton, so it has a weight of 20, is floating on liquid. Guys, when they say it's floating on the liquid, immediately I can say the buoyancy force also is going to be 20 Newton. The reason is because the object is floating. So the weight is cancelled by the buoyancy force. As shown, 40% of the block is unsubmerged. Oh, it's very important. 40% is unsubmerged. So if the volume of the object is V, 60% 60% of the volume of the object is uh, submerged, and 40%, 0.4 V, unsubmerged, as mentioned. Okay. If the density of liquid is 900 in SI units, find the density of the block. Okay, now it's very useful if we use the last ratio. Rho prime, density of the object divided by density of the liquid, is the volume of the submerged part divided by the volume of the object. Let's use this relation. On the other hand, I know that here the submerged part, V1, has a volume of 60% of the volume of the object. So V1 divided by V is supposed to be 6 over 10. It's very good. And on the left side, I have also rho prime, density of the object, which is my goal, divided by density of the liquid. Good, so we are done. And we can easily find the rho prime. How? Rho prime is going to be 0.6 times 900. 540 kilogram per cubic meter. This is the density of the object. Now let's go back to the previous case and learn the benefit of that relation. Here the object is floated. For the floating object partially submerged, the ratio of rho prime over rho proved to be V1 divided by V. V1 is the volume of the submerged part, and it's less than the total volume of the object. So this fraction has upstairs less than downstairs. So this fraction is less than 1. Accordingly, rho prime over rho is less than 1. So rho prime is less than rho. So when the object is floating, rho prime, density of the object, is less than the density of liquid. The other is the fully submerged object. I can use that ratio again, but V1 is the same as V because it's fully submerged. So this ratio is 1. If it is 1, rho prime is equal to rho, like a submarine or a fish. But for a sunk object, the buoyancy force is not enough to hold the object, to float it or suspend it. So it sinks. We expect rho prime to be larger than rho, like a piece of a stone or metal in water. The water has the density of less than needed, less than the object, so cannot hold the object like a piece of wood. So it sinks. That's all. Now get ready for a few challenging cases. I have a beaker filled with a liquid and they are over a weighting scale. What's your expectation to read over the screen? Yes, that's correct. You may expect the weight of the liquid and weight of the beaker. B here stands for beaker. Okay, that's right. The second is when you also have a floating wooden block on the liquid. What do you expect to read here? Here I have weight of the liquid, yes. Weight of the beaker, yes, of course. And, the weight of the beaker. And finally something. That something is the buoyancy force. The buoyancy force here acted on the block to hold it and float it over the liquid has a reaction according to the Newton's third law. That reaction is exerted at the bottom of the beaker and sensed by the weighting scale. So here I have the buoyancy force. But incidentally, the buoyancy force as the object is floating on the liquid is also equal to the weight of the block. So why not? Here I can write the weight of the block instead of the buoyancy force. But keep in mind that the buoyancy force here is exactly the weight of the block. The last is when you suspend a metal block. This metallic block actually has a very high density and it will sink if I leave that. But I've held it by a rope. What do you read on the screen? I start with weight of the liquid, weight of the beaker, and something. That something is always, as usual, the buoyancy force. Why? Because there is a buoyancy force acted on the block anyway, even if it sinks. And this buoyancy force is reflected back and the reaction is back downward to the bottom of the beaker, and it's sensed here. But you know that this buoyancy force is less than the weight of the block. So this buoyancy force cannot be substituted by the weight of the block. It's forbidden. The reason is that as the object is suspended here, it's not just because of the buoyancy force. It's also a tension of the rope helping that. So here I finalize it. Weight of the liquid, weight of the beaker, and finally just the buoyancy force. That's all. Go to the next case. This is very easy one. It's very similar to the middle case in previous slide. I have a boat here, some liquid and a beaker. What's your expectation? Immediately you will say weight of the beaker, weight of the liquid, and weight of the boat. BO here is boat. Okay. Then I have an additional load, a piece of a stone here in the boat and on the boat anyway. And the boat is holding that and can suspend it. What do you expect here? Weight of the beaker, weight of the liquid, and here I have buoyancy force. The reaction of the buoyancy force, the back down to the beaker, and then it's sensed here. Yeah. But can I write the buoyancy force is equal to the weight of the boat and weight of the stone? Yes, you can. It is, because it's floating. So here you are allowed to write it as the weight of the boat and the weight of the stone. Keep in mind they are totally equal to the buoyancy force here supplied by the liquid to hold the system. Now I have a challenging question for you. Let's remove the stone and release it to sink. Here the stone can touch the bottom of the beaker. What do you read on that? It's very interesting. Okay, I have here the weight of the beaker, weight of the liquid, and weight of the boat also. But the last is this. Can I here add a W of a stone here as the last term? The answer is yes, you can. Although the stone anyway cannot be held by the boat and it has already sunk in the liquid, but anyway, the liquid, rather than the buoyancy force acting on the stone, also is supplying a normal force to hold it. And they totally add up to be the weight of the stone. So you are allowed to write it. And it's very interesting that the last two cases will have the same answer. Now let's have a problem. A buoy of a uniform cross-sectional area of 0.2 meters square floats in fresh water with 0.75 meter of the height submerged below the water line. As you see, it may be something like a maybe cuboid or cylinder. The density of fresh water is given, 1000 SI units. Calculate the mass of the buoy. Okay, here I believe that the buoyancy force as the object is floating is equal to the weight of the block. On the other hand, I can suppose that the submerged part has a volume of V1. So here if I write W is equal to FB, W is going to be mg, mass of the block, times g. The right side, the buoyancy force. The buoyancy force is the density of liquid times the submerged volume times g. That's all. So let's continue. Here I drop the g. I hold m here. On the left side, my goal, mass of the buoy. On the right side, density of the water, and the V1, the submerged volume. Let's say it has a uniform cross-sectional area, like a cylinder. A cylinder of, let's say this is H, okay? A cylinder of cross-sectional area of A and height of H will have a volume of A times H, okay? So here for V1, I can write it as A times H. H is the height given here and A is 0.2 meters squared. That's all. So it's A, H. Done. We can multiply them. 0.2 times 1,000 will be 200, and 200 times 0.75 is 150, so it's 150 kilogram. The next part of the question is very interesting. Now the buoy is placed in seawater of greater density than freshwater. Explain the change, if any, in the submerged height of the buoy. Okay, the buoyancy force is density of the liquid times the submerged volume times g. On the other hand, here is equal to the weight of the block, weight of the buoy. Here it is constant. In this experiment, it won't change. If this is constant, the right side must be constant. G is always the same in this experiment, but the density of liquid now is going to be greater. Larger density needs less submerged part because we should multiply them to find something constant. Rho V1G is constant. The larger rho needs less V1 to have the same product. So here we believe that it will have less submerged part. So the answer could be like a smaller volume is needed to displace the mass of seawater equal to the mass of the buoy. Hence, a smaller height of the buoy will be submerged in seawater. Let's go to the next question. A metal with a density of 4 times that of water has sunk in a beaker, as shown. Okay, it has a very large density, 4 times that of water. If the metal has a weight of 40 Newton, so let's say this is the weight of the metal and it's 40 Newton, I'm looking for the normal force acting on it at the bottom of the beaker. You know that the buoyancy force is not enough to hold the object. So rather than the buoyancy force, we need a normal force to cancel the weights. Totally, I believe that the normal force plus the buoyancy force will be equal to 40. Okay, now let's go over the values to find it. It's a very challenging question. Look here, guys, you know that let's suppose again that the density of the liquid is rho and density of the object is rho prime. On the other hand, I know that rho prime is 4 times of rho. It's given in the question. Now, the weight of the object is rho prime Vg. Rho prime is density of the object, V is the volume of the object, and it's multiplied by G, the weight of the block. On the other hand, the buoyancy force is rho times Vg. Rho is the density of liquid times the volume of the object times G. This volume is the same as this volume. The reason the object is fully sunk, so it's expected to have the whole volume. Okay, now let's continue like that. We know that rho prime is 4 times of rho. Compare these two relations. V is the same V, G is the same G. If rho prime is 4 times of rho, so W is 4 times of the buoyancy force. So I believe that the buoyancy force is W over 4, a quarter of the weight. Good. So buoyancy force is a quarter of weight. On the other hand, I know that the object is acted by zero net force because it's at rest. So the buoyancy force plus the normal force will be equal to W. Now I can substitute the buoyancy force by W over 4. And then N plus W over 4 is W. I take the W over 4 to the right side, so N is equal to W minus W over 4. So it's 3/4 of W. You see that I know the W because it's given in the question to be 40 Newton, so it's 3/4 of 40. It seems to be 30 Newton. Thank you for watching this video and thank you for your attention. Take care. See you.